All right, so we've got these two papers all about how to make LLMs better at reasoning.
Yeah.
Seems like a pretty hot topic right now.
Oh, yeah, definitely. Especially for researchers and engineers who are, trying to build AI systems that can actually, like solve complex problems.
Right, like it's one thing to have an LLM that can, write a poem or summarize a text,
Right.
but it's a whole other challenge to get them to think logically and make decisions based on, actual reasoning.
Exactly. And that's really what these two papers are getting at. Like, how do we make these LLMs more well-reasoned?
So what really caught my eye is that both of these papers are exploring ways to improve reasoning without needing those massive labeled data sets,
Yeah.
like the ones we usually rely on for training.
Yeah.
That feels like a real game changer.
Yeah, it's pretty wild. Like, they're basically saying, can we get these LLMs to sort of bootstrap their own reasoning abilities? Can they learn to think more effectively on their own without us having to, like, spoon feed them all the answers?
Okay, so let's start with the first paper. Language models are hidden reasoners, unlocking latent reasoning capabilities via self-rewarding.
Yeah.
Even the title is kind of mysterious. Like, what are they getting at with this hidden reasoners idea?
So the basic idea is that the ability to reason is already kind of lurking within these LLMs.
Mm.
Like it's there, but it hasn't been fully activated. It's latent. And their method, which they call LaTRO, is all about kind of coaxing that reasoning power out.
Okay, so it's like we've got these brilliant but sort of untapped minds, and we just need to find the right way to unlock their potential.
Right, exactly.
So how does this LaTrO thing actually work?
Well, it all comes down to how the LLM explores different reasoning pathways.
Pathways.
Yeah, like imagine you're trying to solve a math problem.
Okay.
With LaTRO, the LLM is encouraged to try out different ways of solving it. Different steps, different operations, kind of like exploring different routes on a map to find the best way to get to a destination.
I see. So instead of just like blindly guessing the answer or following a single pre-programmed path, it's like the LLM is actually trying out different approaches and seeing which one makes the most sense.
Right, exactly. And here's the really clever part. The LLM actually acts as its own judge.
Its own judge.
Yeah, it evaluates the likelihood that each reasoning pathway will lead to the correct answer. Like, is this step likely to get me closer to the solution, or is it taking me in the wrong direction?
So the LLM is both generating the reasoning steps and evaluating their quality like it's wearing two hats.
Right, and that's what they call the self-rewarding mechanism. The LLM is essentially rewarding itself for following pathways that seem more promising.
Okay. I can see how that would be really powerful. Like, it's learning to guide its own thinking, but doesn't that kind of create a risk of bias?
Mm.
Like, if the LLM is only rewarding itself for following certain paths, it could end up getting stuck in a rut or developing blind spots.
Yeah, that's a good point, and the researchers definitely acknowledge that potential risk, but the results actually show that LLMs can be surprisingly good at assessing the quality of their own reasoning, at least, within the specific tasks they tested.
Okay, so they're not claiming that this solves all the problems of AI bias,
Right.
but it seems like a step in the right direction. Like, maybe these LLMs are more capable of self-reflection than we give them credit for.
Yeah, and from a practical standpoint, the results are pretty impressive too.
Okay, let's talk numbers then.
So they tested LaTRO on a benchmark dataset of math word problems called GSM-8K.
Okay, I've heard that one. It's like a standard test for seeing how well AI systems can handle, like those tricky word problems that you might see in elementary school.
Exactly. And across different LLM sizes,
Mhm.
from smaller models like 3.5 mini to larger ones like Llama 3.18B, LaTRO significantly outperformed baseline models, and it even beat out standard supervised fine-tuning methods.
Wow, so this isn't just like a small incremental improvement. We're talking about something that's actually pushing the state of the art forward.
Right, exactly. And on average, they saw a 12.5% improvement over the base models and a 9.6% improvement over supervised fine-tuning.
Okay, so 12.5%, that's pretty significant,
Yeah.
especially in a field like AI where progress can sometimes be measured in like, fractions of a percent.
Right, it's definitely a noticeable jump.
But how does this actually translate into solving real problems? Like give me an example.
Sure, so imagine you're building a chatbot to help customers with basic financial calculations.
Yep.
A standard LLM might struggle with a seemingly simple word problem, like if you deposit $500 into your account and then withdraw $200, what's your remaining balance?
Yeah, even though it's simple arithmetic, the way it's phrased could totally trip up a standard LLM.
Exactly. But with LaTRO, the model breaks the problem down strategically. It would reason, okay, depositing means adding money, 500 plus 200 equals 700. Withdrawing means subtracting money. 700 minus 200 equals 500. So the final answer is $500.
Huh. Oh, I see. So it's not just about getting the right answer. It's about showing its work, like
Yeah.
demonstrating that it actually understands the steps involved in the reasoning process.
Exactly. It's like giving the LLM a set of mental tools to tackle these problems in a more human-like way.
That's pretty cool. But I'm
Yeah.
also wondering about the computational cost of all this extra reasoning.
Yeah.
Like, wouldn't all these different pathways make the LLM slower and more expensive to run?
That's a great question, and it's one of the things that the researchers explored in their paper.
Okay.
And what they found is that LaTRO actually shows promise in compressing the reasoning process.
Compressing it.
Yeah. So instead of doing all the heavy lifting during inference, a lot of the computational burden is shifted to the training phase.
Oh, so it's like it's doing the hard work up front so
Yeah.
that it can be more efficient later on.
Right, exactly.
That's a pretty clever approach, especially for researchers and engineers who are always looking for ways to optimize performance. Okay, so far we've got LLMs becoming better reasoners through self-evaluation. But now I want to move on to the second paper because this one brings in a whole other dimension, visual information.
Oh, yeah. This one's really interesting. It's called LLM2CLIP. Powerful Language Model Unlock Richer Visual Representation.
Okay, so we're talking about LLMs and CLIP now. For those who might not be familiar with CLIP, can you give us a quick rundown?
Sure. So CLIP is a model that's really good at connecting images and text. Like it can learn to associate images with the words that describe them.
Okay, so it's like a visual dictionary or a search engine that understands what's actually in the pictures.
Exactly.
So how are they bringing LLMs into the mix? Like, I feel like LLMs and CLIP would be a match made in AI heaven.
You would think so, right? But it turns out it's trickier than just plugging an LLM into CLIP.
Oh, really? What's the catch?
So the researchers wanted to use the LLM's vast knowledge base to help CLIP process more complex images and captions, like really understand what's going on in a scene.
That makes sense, but I'm guessing there were some technical hurdles along the way.
Yeah, the main problem is that LLMs aren't designed to generate the kind of output that CLIP needs for its training process. CLIP relies on this thing called contrastive learning, where it compares images and text and tries to find the best matches.
Okay.
But standard LLMs, they're not really built for that. If you just try to swap out CLIP's text encoder with an LLM, you actually get worse performance.
Oh, so it's not as simple as just like plugging and playing.
Nope.
So how did they solve this problem?
They came up with this really clever two-step process called LMLM2CLIP.
LLM to CLIP.
Okay, I like it. First, they used this technique called caption contrastive fine-tuning to basically teach the LLM how to distinguish between different image captions.
Okay, so they're making the LLM a caption expert.
Exactly.
And then what?
In the second step, they use this fine-tuned LLM as a teacher to guide CLIP's visual encoder.
So it's like the LLM is saying, okay, CLIP, here's how you should be thinking about these images based on what I know about captions.
Right, exactly. And this way, CLIP benefits from the LLM's knowledge without having to train the entire massive LLM itself.
That's really smart. Like they're finding ways to get the best of both worlds
Right.
without sacrificing efficiency.
Exactly.
So did this approach actually work? Like, did they see any improvements in CLIP's performance?
Oh, yeah, the results were pretty amazing.
Yeah.
LLM2LAP boosted the performance of a state-of-the-art CLAP model called EVA02 by a whopping 16.5%.
16.5%? Wow, that's huge.
Yeah, and it did this on both long text and short text retrieval tasks, so it's not just good at one specific type of caption, it's good across the board.
Okay, so give me a concrete example. Like, how would this improved performance be visible in a real-world application?
Let's say you're building an image search engine that needs to handle complex queries. Like
Yeah.
you show it a picture of a busy city street with lots of different things going on.
Right.
A standard LLM might retrieve a caption that's way off, like, a dog running through a field or something.
Right, because it's just picking up on like the most obvious object in the image.
Right, but LLM2CLIP, thanks to its enhanced caption understanding it would return a caption that's much more accurate and detailed, like a bustling city street scene with pedestrians, vehicles, and a dog being walked on a leash.
Oh, wow. So it's not just recognizing objects, it's understanding the relationships between them and like the overall context of the scene.
Exactly.
That's really impressive. But didn't we talk earlier about how incorporating LLMs into these models can make them computationally expensive to train?
Right.
Like I'm imagining that all this extra processing power must come at a cost.
It's a valid concern, but the researchers behind LLM2CLIP were very mindful of that, and they found that the training overhead for LLM2CLIP is pretty much the same as fine-tuning a standard CLIP model.
So we get all these performance gains without a significant increase in computational cost. That's amazing.
It's pretty remarkable, and it really speaks to the ingenuity of their approach. They found a way to make these powerful models more accessible and practical for a wider range of researchers and engineers.
Okay, so just to kind of recap for a second, we've got two very different approaches here, both aimed at improving LLM reasoning, but both also demonstrating that we might not need these massive labeled data sets that we've traditionally relied on.
Right.
Like these models are learning to think more effectively on their own, which is both exciting and a little bit mind-blowing.
Yeah, it really challenges our assumptions about how AI needs to be trained.
Yeah.
Maybe these models are more capable of independent learning than we give them credit for.
Right. And that raises a lot of interesting questions about the future of AI. Like if we can unlock this ability for LLMs to reason more effectively on their own, what other capabilities might they develop?
It's a really exciting time to be working in this field, that's for sure.
All right, so let's dig a little deeper into the technical stuff behind LaTRO and LLM2 concurrently. For all those AI researchers and engineers out there who are eager to really understand how these things work.
Sure, let's start with LaTRO and how it uses these variational approaches to optimize reasoning.
Variational approaches.
Yeah, basically it's about giving the LLM more flexibility in how it explores different reasoning pathways. Instead of forcing it to choose just one path, it encourages it to consider a whole distribution of possibilities.
Okay, so it's like giving the LLM a bit more freedom to kind of wander around the problem space and explore different options.
Exactly. And the goal is to find the most likely route to the correct answer, not just any old route.
Okay, that makes sense. So for our listeners who are really digging into the code, what are some of the implementation details they should be paying attention to?
One of the key things is how LaTRO manages the length of these reasoning pathways during training. You want to give the LLM enough room to explore, but you also don't want it to get bogged down in these really long and complex chains of reasoning.
Right, it's like finding that sweet spot between exploration and efficiency.
Exactly. And the researchers had to come up with some clever ways to kind of encourage the LLM to complete its reasoning within a certain number of steps.
I see. So it's like setting boundaries for the LLM's exploration, making sure it doesn't get lost in a rabbit hole.
Right. And they did a bunch of experiments to figure out what those boundaries should be. Like how many tokens the LLM actually needs for effective reasoning.
And what did they find?
Well, for the types of problems they were working with, like those grade school math problems, it seems like around 500 tokens is a good sweet spot.
Okay, so that's useful information for anyone trying to implement this in their own work. Knowing that there's a reasonable limit to the token count can help with optimization.
Absolutely. And they also found something pretty interesting. Even though LaTRO is mainly focused on improving reasoning during training, it can still benefit from techniques that are applied during inference.
During inference?
Yeah, like self-consistency, which is a way of getting multiple predictions from the LLM and then kind of combining them to get a more robust answer.
Oh, so it's like adding an extra layer of checks and balances to make sure the LLM is really on the right track.
Yeah.
Okay, so we've covered some of the key technical aspects of LaTRO. Now let's switch gears and talk about LLM2 CLIP. One of the big challenges they had to overcome was figuring out how to make the LLM's output compatible with CLIP's training process.
Right, because standard LLMs, while they're great at understanding language, they don't naturally produce the kind of output that CLIP needs for its contrastive learning. CLIP is all about aligning images and text, and it needs features that can effectively discriminate between different captions.
Right, it's like CLIP needs a specific kind of language that's tailored to visual information.
Exactly, and that's where the caption contrastive fine-tuning comes in. That's the first step in the LLM2 CLIP process.
So how did they do that? Like, what's the secret sauce in their fine-tuning method?
Well, they used a few different tricks. One is they expanded the LLM's attention mechanism to be bidirectional.
Bidirectional.
Yeah, so instead of just looking at the words that come before a given word, it can also look at the words that come after it. It gives the LLM a wider context to work with.
Oh, I see. So it's like giving the LLM a more holistic view of the caption.
Exactly. And another technique they use is called masked next token prediction.
Okay, I've heard of that one. It's like you mask out certain words in a sentence and then train the model to predict what those missing words are.
Right. It's a really effective way to teach the LLM about the structure and meaning of language, especially in the context of captions.
So they're basically giving the LLM a crash course in caption comprehension.
Exactly.
And then for the actual contrastive learning phase, they use a supervised SimCSE loss.
Right, which is a way of measuring how similar or different various captions are. They train the LLM on a data set that has pairs of original captions and then these augmented dense captions for the same image.
Okay, so the LLM is learning to distinguish between captions that are basically saying the same thing, even if they're worded differently or focus on different details. It's fascinating how they're using contrastive learning to kind of fine-tune the LLM's understanding of captions. But I'm also wondering, did they have to make any compromises to the LLM's overall language abilities to achieve this?
That's a great question, and it's something they were very careful about. They didn't want the LLM to become too specialized in captions and lose its ability to understand language more broadly.
Right, we don't want to create a one-trick pony.
Exactly. So they balanced this caption-focused training with training on more general text data to make sure the LLM retained its broader language skills.
Okay, so it's like they're teaching the LLM to be bilingual fluent in both general language and the language of captions.
Right, and this approach really paid off after just one epoch of this caption. Contrastive fine-tuning the LLM's ability to distinguish between captions improved dramatically.
One epoch.
Yeah, and it actually outperformed some state-of-the-art CLAP models that were trained on much larger data sets.
Wow, so it's not just about the size of the data, it's about the quality of the training methods. Okay, so for those who are eager to try out LLM 2CC LAP, what are some of the practical things they need to keep in mind? Like I'm imagining that incorporating a large LLM into CCLAP could be computationally expensive.
You're absolutely right. Computational cost is always a consideration, but the researchers behind LLM2 CLAP made some smart choices to address this.
Like what?
Well, during the caption contrastive fine-tuning stage, they used a technique called LoRa, which is a way of efficiently fine-tuning large language models without needing a ton of memory.
Okay, so LoRa helps them to keep the computational footprint manageable.
Exactly. And then during the main LLM2 CLAP training stage, they froze the LLM's gradients.
Froze the gradients.
Yeah, so basically they're saying, okay, LLM, you've done your job now. Just sit tight while we train the CLAP visual encoder.
Oh, I see. So the LLM is like a teacher who's given the student all the knowledge they need, and now the student can go off and practice on their own.
Exactly. And by freezing the LLM's gradients, they significantly reduce the computational burden.
Smart move, and to make things even more efficient, they pre-extracted all the text features from the training data using the LLM and stored them in memory.
Right, so they don't have to run the LLM repeatedly during training, which saves a lot of time and resources.
So they're basically front-loading the LLM's contributions to make the overall process smoother and faster.
Exactly. And with all these optimizations in place, the training cost of LLM2 CLIP becomes comparable to fine-tuning a standard CLIP model.
That's really impressive considering that we're now incorporating the power of an LLM.
Right. It's a win-win situation. You get the performance benefits without the computational overhead.
This feels like a huge win for researchers who might not have access to, those massive supercomputers that some of the big tech companies have.
Absolutely. It democratizes access to these powerful techniques.
Okay, so we've gone pretty deep into the technical details of LaTRO and LLM2 CLIP, and I think our listeners who are AI researchers and engineers now have a good understanding of what makes these approaches so innovative. But as we wrap up this part of our deep dive, I want to kind of zoom out a bit and talk about the bigger picture. If we can unlock the ability for LLMs to reason more effectively on their own, what does that mean for the future of AI development?
It's a question that opens up a world of possibilities, some exhilarating and some that require careful consideration. Imagine a future where AI systems are no longer just passive tools that we program, but active collaborators that can learn and reason alongside us.
That's a really profound thought, and I think we need to unpack that a bit more. So we were talking about, this idea of LLMs that can actually reason on their own.
Yeah, like what does that even mean, for the future of AI?
It's kind of mind-blowing when you really think about it.
Totally, and especially for researchers and engineers, it's like a whole new frontier.
So far, we've been focusing on how these, enhanced reasoning abilities could improve things like problem solving and image understanding.
Right.
But I'm curious to explore how this might impact other areas of AI development.
Yeah, for sure.
What are some of the other areas that you're excited about?
Well, one that I think has huge potential is scientific discovery.
Oh, yeah. Like imagine LLMs that can not only process like tons of scientific data,
Right.
but also actually reason about it.
Yeah.
Make connections, generate hypotheses.
Exactly. Like it could revolutionize fields like medicine, materials, science, you name it.
It's like having an AI research assistant that can sift through all that data
Yeah.
and be like, okay, here are the most promising avenues for investigation.
Yeah, and it could free up human researchers to focus on the more, creative and strategic aspects of their work.
Right, like the big picture thinking.
Exactly.
And it's not just about processing existing knowledge, right?
Yeah.
These LLMs could also contribute to the design of new experiments, like helping scientists figure out how to test those hypotheses and gather new data.
Yeah, like in a more targeted and efficient way.
So we're talking about accelerating the pace of scientific progress,
Absolutely.
which has huge implications for, solving all sorts of problems.
Huge.
And it's not just limited to science, right?
No, not at all.
Like think about engineering, for example,
Yeah,
where, complex systems design and problem solving are so important.
totally. LLMs with better reasoning abilities could revolutionize how we design everything from bridges to spacecraft.
It's like having an AI engineer that can help us optimize for performance and safety and efficiency.
Exactly.
Okay, so we've got science, we've got engineering.
Right.
Are there any other fields that you think would be particularly impacted by this?
I think pretty much every field would be affected in some way.
Yeah, it's hard to imagine an area where better reasoning wouldn't be beneficial.
Exactly.
But one area that I'm personally really fascinated by is the potential for these LLMs to enhance human creativity.
Oh, yeah, that's an interesting one.
Like we've already seen AI systems that can generate art and music and write stories.
Right.
But imagine a world where those AI systems can actually collaborate with human creators, helping them to brainstorm ideas, explore new concepts, and really push the boundaries of artistic expression.
Yeah, it's like having an AI muse.
Right, exactly, like a source of inspiration and new ideas.
And I think the key is to view these AI systems not as replacements for human creativity,
Right.
but as partners or collaborators. They can offer a fresh perspective, generate unexpected ideas, help us break free from our own limited thinking.
It's like a true meeting of the minds, human and artificial intelligence working together to create something truly new and innovative.
Exactly.
Okay, so to kind of wrap up our conversation today,
Yeah.
we've explored these two amazing research papers that show how LLMs can become more powerful reasoners.
Right.
We've talked about the technical details, the potential applications, and the broader implications for the future of AI.
And I think it's safe to say that we're just scratching the surface here.
Totally. Like this is just the beginning of what's possible with these models.
Absolutely.
So for all our listeners out there who are AI researchers and engineers,
Yeah.
I hope this deep dive has given you some new ideas and some inspiration to keep pushing the boundaries of what's possible.
And for everyone else, stay curious, stay informed, and keep asking questions about the role of AI in our world.
Thank you for joining us on this episode of The Deep Dive.
Yeah, thanks for listening.
We'll be back soon with more fascinating explorations of the world of AI.
See you next time.
Until then, keep those AI neurons firing.